this person highlights a really good point, because he talks about talks about AI psychosis, which I know is a thing. That's not what this is. Bro, I've been way before AI came out. I was down my rabbit holes. Okay, no disrespect, right? That's not even about this. I want to appease this partially. I won't show everything I got. I won't show all my math, this and this and that. I will show I will show my code so that you can see the environment. This is, I've never done this. I wanted to show a step of, at least you can see what I've got in there, so that the results themselves, and with redacting the important stuff that is proprietary, so you can see the outputs are not just like randomized and whatever, from like some obscure fudged code. And like, you may still be skeptical. People may still be like, nah, I don't believe it, this and this and that. I'm sure that will happen. And maybe you even catch things that I should do differently. Put them in the comments. I'll try to appease what I can. But I'll show my notebook right now and show the code, and then show the outputs, and I'll even show some of my other stuff. Okay. So I'm here in the notebook that I was talking about, and you can also see I've been doing just like an infinite amount of testing on just like checking the noise, the differences of recovery, entropy, and the fidelity. I mean, I've been doing a lot of testing to see just how my system works as a whole, and if it will be applicable to the current systems. So I've been doing a lot of this, but anywho, I am going to, here's the code. Okay, nothing weird. Obviously I redacted the stuff that's important. The simulation will be for 2 million qubits. If you want to pause it and look now, you can. So at least you can see it's not bizarre and like something uncouth. Anyway, I'm gonna run it and we'll see the outputs. So obviously okay, great. So here we go. Simulation complete. Redacted logic executed successfully. Entropy drift over time. You can see it's all here. Okay, it's all here. You know what? I'm gonna pause this, edit some of the code, and have even more outputs put. Okay, and further we move on to, I want to show a few things here. You'll see a few tests here. I also want to show the expansion of the qubits themselves, in chunks, of course. And, well, you can kind of see it for yourself. Pause the video, look through it. You can see the parameters I've set for the environment is not, I don't know, fugazi. Is there anything? Obviously, I've redacted my logic, so you can't just take that. But I don't know. I feel like this is a step forward. I've never done this. Okay, when I run the cell. That was quick. Entropy session hash. You can see the line here. You can see the fidelity versus the drift, the spectrum. Okay. Modeled 500,000, 750, a million, 1,500. And you can kind of see how it's, I don't know. Is this enough? Is this not really enough? Tell me if you want more. And you know what? I just wanted to show one more practical simulation here after the ones you've just seen to, I guess, to show the capabilities of expansion. Obviously using, obviously simulate it, but you can see it. I wanted to simulate it according to how these quantum systems at scale might behave in terms of stability across 1 million qubits. Obviously, I've redacted my proprietary aspects, but I want you to show the environment to at least, I don't know, offer a fractured measure of confidence For those who are not familiar with what I'm doing, I'm using a dampening model that accounts for decay over time and like energy dispersion and like a certain recursive correction. Although the main proprietary logic, as you can see, has been redacted. The goal really is to test how many of these simulated qubits remain stable under those conditions using a memory-safe chunking system. And at the end, we're calculating energy usage from like two perspectives: one, for Planck's constant for like theoretical physics grounding, and then two, for more engineering estimates, like reflecting what an actual device might consume. As you can see here in the constants, I've labeled them and added decay rates and whatnot so that there is a more stabilized for what a real system might encounter. We're going to test for 1 million qubits. As you can see, I've put all the things here. And this should output exactly what we want. So hopefully this is at least some measure of proof here. I'm going to run the cell. It won't take long. Okay. You watch them in chunks of 100,000. Tests complete. Total qubits simulated 1 million. The stable amount is about 989,358, or 98.93%, which is usually more than usual. We usually get about 98.80 to 98.55 or so. The amount of energy used is this approximate, and as following the same here, in about 3.8 seconds. Obviously had it print that it's been redacted for proprietary protection, but at least you can see sort of what I'm utilizing here, so that I'm not just full of hot gas. Does this help at all?